guys, starting chapter 5 today, we're going to cover section A. So if you want to follow along in your books, we're going to start talking about some chemical bonds. Okay, we've been talking a lot about the periodic table, and I've alluded to a lot of this stuff, but now we're going to really get into it. That's a model of a compound, of a single molecule, and each of those different colored circles is a different element. The connections between those things represents the chemical bonds. Okay. So a chemical bond is an electrostatic attraction between the atoms, and it can happen either by electrons being transferred or by them sharing electrons. Okay, electrostatic. You know what static electricity is, right? It's when stuff like kind of sticks to you because it's real staticky, or those little shocks you feel. That deals with electricity and the charges of the particles in these atoms, the positive protons and the negative electrons. If those are out of balance, there's an actual charge to the atoms, and those opposite charges attract to each other. The valence electrons on the outside, even if it is a neutral element, there's still some kind of attraction going on there. So when we hear the word electrostatic attraction, it really has to do with those charges. A compound, so that's a picture of a compound there, a pretty complex compound, is when two or more elements are sharing a chemical bond, okay? And it can just be a very basic, like O2. That's two oxygen atoms. That's considered a compound. Sometimes it's also referred to as an element just because it's elemental oxygen, different story. H2O, two hydrogens, one oxygen, but it can be even more complex. Proteins are still compounds, but they have longer strings of letters and more elements to them, higher ratios. Okay, so why are there so many different compounds? Elements are typically unstable when they aren't bonded because of those varying numbers of valence electrons. So when they become combined with other elements in a compound, they just kind of relax. They're just more comfortable because they're definitely more stable. So we've talked about this before. We've talked about this rule of octet in the last chapter a little bit. And this is just the idea of that instability due to those valence electrons. Those elements are most comfortable and they're most stable, those atoms, when they have a full 8 electrons in their outer shell. And that's something that's known as the octet rule, okay? So we've talked about some examples there. So these atoms that are short of electrons are looking for extras, or maybe if they only have a couple, they're looking to give them away. And they match up with things that need like that special magic 8 number. And so there's a lot of matching of elements with valence electrons that total up to 8 between the two elements there, okay? Helium and hydrogen are exceptions to this because they only have one energy ring, and that energy ring only can hold 2 electrons. So they only have 2 valence electrons maximum. So they don't really follow this octet rule, but it's the same idea, okay? So you can see a picture of water here. Let me get my pen out. Use this color. So here's one hydrogen, here's another hydrogen, and they each have 1 electron. They're looking for an extra one, okay? Well, here's oxygen, which has 6 electrons. It needs 2 extra. And so if you take the 2 from the hydrogen, add it to the 6 of the oxygen, now suddenly we have 8 total if you consider them sharing. So the hydrogen is now comfortable because they have their full 2, okay? And the oxygen is now comfortable because it has its full octet rule right there. And so that's why that compound in particular works really well. These bonds can be made by either sharing the electrons or actually transferring them. This would be an example of sharing the electrons, okay? So there's different types of bonds depending on what's happening. A covalent bond occurs between atoms that have a very similar electronegativity. Remember that affinity to hang on to those electrons. If it's similar, they tend to just share the electrons, not actually transfer them. And this happens most often between nonmetals, okay? So the water that I just showed you, that's between hydrogen and oxygen. Those are both nonmetals. That is an example of a covalent bond. They are just sharing those electrons, okay? Sodium chloride, which is one that I've shown you several times, that's what's known as an ionic bond, okay? They have very different electronegativities. The chlorine has a much higher electronegativity than the sodium. Plus, this type of bond typically happens between a metal and a nonmetal. So sodium is a metal, chlorine is a nonmetal, and so when those get together, what happens is that single electron, valence electron from sodium leaves, and it literally transfers over to the chlorine, okay? I'm not sure why they're only showing 6 electrons in this. It's just how the drawing is. I'll just add in a couple more. You guys know this. Chlorine has 7 valence electrons, okay? So once that one electron is transferred over to the chlorine, now it has that magic octet of 8, okay? But since the electron actually left the sodium is left with a positive charge, okay? Since the chlorine actually gained an electron, it's left with a negative charge. They both become ions, which is why this is called an ionic bond. They are stuck together, that positive and that negative attracts, but individually they are considered ions, okay? There's another kind of bond, it's known as a metallic bond. We're really not gonna talk about that much. It deals with a lot of those transition metals that we just kind of don't talk about until you get into higher chemistry. In the metals, though, the electrons are kind of free to move around a little bit from one atom to the next. They don't really share or transfer ionically. They're just kind of bouncing around, which is weird. But then that bond, the metallic bond itself, is that attraction between the metal atoms and those free electrons that are moving around, okay? That's really as far as we're going to go into the metallic bonds. We will talk a lot more about the covalent and the ionic bonds in the next section, though, okay? So this is a picture of the Hindenburg. This is a blimp that used to fly around, and it actually exploded. And it's just a very big example of the fact that unbonded elements are very different than bonded elements. In class, I will show you how sodium reacts with water. Sodium by itself is very volatile. Sodium, when it's mixed with chlorine, it's just salt. It's not a big deal. It's super stable. It's super safe. Chlorine gas by itself is poisonous. But again, when it's with sodium, it's fine. So this is hydrogen. Okay, we drink water all the time. There's hydrogen in water. But hydrogen gas by itself, when it's not bonded with something, is incredibly explosive. And so this blimp was filled with hydrogen instead of helium because there was a helium shortage. The inside part where the people were wasn't actually filled with hydrogen, but this like outer skin was filled with hydrogen. And it's not fully known, but the kind of agreed upon theory is that it started leaking and a spark ignited it, and this thing just blew up, and a lot of people died as a result. So that's just hydrogen reacting to a spark because it's so much more reactive. When it's mixed with water, totally stable, okay? These unbonded elements have much different properties than when they are bonded. And that's it for section A. See you later.